Hello, in this video I will present you what I did about the operational semantics of Lingua Franca in MOCML. This is my comprehension so far, but it can be changed, of course. So the basic idea is that there are three dimensions of time: the logical time, the microsteps, and the causalities inside the microsteps. And these different dimensions of time are actually constraints themselves and between themselves. So I will take an example of the auto-where example of Lingua Franca to illustrate the different dimensions of time. So what I did to express the semantics between these different dimensions is that first I defined some clocks on the model. So basically a clock is a totally ordered set of instants. Okay, so here you see a clock A with 3 instants which are actually ordered. All these exec here are some clocks which are associated to the modeling element here, some reactions. Okay, so reactions can execute. And these clocks actually represent the events of interest that we want to see in the system at runtime. We also had some other event of interest, like for example the update of an output port or an input port. And of course we define some constraint between them, since the update of a port cannot occur at any time. It occurs necessarily, in our case, at the same time than the execution of the reaction. Okay, in the same way, there is a constraint between the update of an output port and the update of the connected input ports. We decided to make it at the very same time also. And between the update of an input port and the execution of the corresponding reactions, we decided to have a precede relations here. Okay, what are these relations? This is some constraints in CCSL, so the equal sign specifies that for each instant of a clock there is another instant of the other clocks, which is actually synchronous with it. While the precede relations specifies that here B happens because A. Okay, so there is a bijection between the instance of B and the instance of A, but they do not arrive at the same time. There is a precedence between them. Okay, so basically what does it mean? It means that when a reaction executes, then it will produce an update on the output port and the corresponding input ports, and then later on it will allow these reactions to execute. We did that for the different clocks. We constrained all of them. And we add some other event of interest, like for example the starts of either timers or actions here, timed actions. Okay, so this starts means that it schedules actually new actions to be done, these following actions. Okay, so there are some constraints between them, like for example the execution of these reactions creates a start occurrence at the very same time that schedules these actions in the next 100 milliseconds. And this is true for all of them. We also have the release of these timed actions. So the release of a timer, the release of an action, meaning that the logical time actually elapsed, so that the corresponding timed concept can release. Once again, we got some constraint between these clocks, like for example the starts happens before release, of course. The release happens because of the starts. This is a bit more complex actually in the implementation, but this is sufficient to understand the idea. And there are also, so for all of them there are these precedes relations, and there are also some relations between the release of a time concept and the next execution. So here the release of this action must happen before the execution of this reaction. Okay, and this is true for all of them. Okay, so basically we put all the constraints like that, and we got last things to introduce, which is the release of a micro time concept. So this logical action in Lingua Franca has no minimum delay specified, meaning that this can occur inside micro steps. And I didn't represent it here, but we have the same kind of constraint between the untimed concept, the causalities, and the microstep concept. And we got the constraint for all of them. I will not detail it here. What is interesting is that we also have some other concept, because actually the superdense time, so representing the logical time and the microstep, is stored into a tuple of two natural integers, current time and current microstep. So this is a classical superdense time. And scheduled actions are stored to an event list, so the classical discrete event list you can think in most of the simulators. So this event list is based on tuple, superdense time tuples, and it's prioritized according to the superdense time order. So we have actually new clocks here, and these clocks are here because this red release and this green releases are actually data dependent. It means that they can occur or not depending on what you have in this event list file. Okay, so it means that we add two clocks, and actually when these clocks can release occurs, the event list is checked and a boolean is returned to specify if, depending on the current time and the current microstep, this actual time concept can release or not. So if it returns true, it can actually release. If it returns false, it has actually to wait. And of course, we have some constraint between these concepts, like for the others. I will speak a bit. So these are the basic ideas. I will speak a bit about the implementation. So this is done in MOCML. MOCML stands for Model of Concurrency and Communication Modeling Language. This is specified at the language level. Okay, it means that I did not wrote all these constraints by hand. Actually, it generated. I will put few slides on that just after. And this is integrated in a specific branch of the GEMOC Studio for formal analysis. This is the link if you want to have a look. Concerning the point 2 specified at the language level, I will just make a quick explanation of what happens inside. So this is an example based on mark graph. So mark graph are, let's say, petri nets without any conflicts. So it's made up with places and transitions, and places and transitions are linked. Here you can see an instance of a mark graph with transitions and place. And this behavior here is actually the CCSL or MOCML representation I just showed you before. And the model is actually the composition of the structure and this MOCML specification. What we did is that we used Kermeta to statically introduce, to weave inside the concepts of the language the runtime state of the model. So here, for example, in the context of a mark graph, the runtime state is the current marking. So we actually wove into each place current marking attributes, so that we can store the state at runtime of the model. Okay, and this is done like that. We actually declare an aspect on the place, and this aspect is an integer which is named current marking here. We also weave into the concept some rewriting rules, which is the classic rewriting rules of operational semantics. For example, here the fire of a transition. So basically the fire of a transition consumes token in the input place and produces token in the output place. Okay, so this is specified like that. So once again, it's an aspect which defines the fire rewriting rules, and which does for each input place current marking -1, and for the output places current marking +1. Okay, so these are the rewriting over the current state of the system. These rewriting rules are actually called depending on the model of concurrency. So the model of concurrency starts to specify at the language level, once again by static introductions, some domain-specific events. So for example, here the firing of a transition that actually, when it occurs, calls the rewriting rules. Okay, it acts like a handle over the rewriting rules. So this is specified in MOCML. So this is an example. In the context of a transition, I define a new event which is fired, and whose occurrences will later on call the fire rewriting rules in the context of the self instance. Okay, so what does it mean? It means that for each instance of transition, it will actually create a CCSL clocks like I just showed before. Okay, so here I got 4 fire clocks, which actually corresponds to the 4 instances of the transition you can see here. And we put some constraints between these clocks the same way. So here in the context of a place, there is a constraint which is the precise relations between the fire of the input place and the fire of the output place, which is shown here on the picture. So it means that I put the self in the context of the place here, and I said that if I'm this place, so it means that this transition must fire before this transition. Okay, and this is the way I actually define the operational semantics of Lingua Franca in the GEMOC Studio, by defining it at the language level, and then it instantiates at the model level. What actually happens is that these representations in MOCML generates a compiler. So this generates a compiler which takes any structure corresponding to the conforming to the language and produce the CCSL specifications that can be interpreted by the time-square tool. And in this time-square tool, I can do different things like model animation, omniscient debugging, exhaustive simulation, etc. I will show it to you in the next video on Lingua Franca. Thank you.